Today we're going to talk about piecewise functions. Piecewise functions are functions that are defined by two or more equations. Each piece of the function is active or applies to different parts of its domain. And remember, domain we always refer to as our x values. So we got to remind ourselves as we're working through all of these that the domain are the x values. So here we see a picture of a piecewise function, and they look a little bit different than anything that we've kind of seen so far. So f of x would be the function f, and we have this little half bracket. We don't have it on the other side, but to show that both of these equations or expressions are part of the function. So the thing about this function is this top one, f minus, x minus 2, is only active when our x's are less than or equal to 0. Once we go above 0 or greater than 0, this is what our function looks like. So it's important to kind of figure that out before we start looking at the graphs or how to make those. But basically, looking over here at this picture, this is the piece that is the less than or equal to 0. And I know that because, remember, our domain are the x values. So when x is 0 or anything that's less, this is the equation that is active. Now I want you to notice that normally when we graph f of x equals x minus 2, we would have had a y-intercept of a negative 2 coming from our b value there. We have a slope of a 1, which would be right here, up 1 over 1, or anywhere on the graph, up 1 over 1. But then we would have gone and drawn a line through all of this with arrows on both sides forever and ever. The way the piecewise works is this right here is telling me where the domain is active. So this function, if it was no restriction, would have kept going after 0. This tells me we're only going to see the line from the 0 and all negative x's going this way. So we stop it, we don't put an arrow on that side, and we have the arrow going this way because it does go on forever on the negative side. I also want you to notice, because this is the or equal to, this is a closed circle. That is definitely a value. When x's are 0, that is the value that comes out. And then when you shift to this one, now we have f of x, which is the same f of x as this, but now it's active as a 2x plus 1 when x's are greater than 0. So again, if I was graphing it just as 2x plus 1, this would be the y-intercept. A positive 2 slope would have gotten me to that point or to that point. And typically we would have drawn it on forever going this way with arrows on both sides. This tells me the domain is only seeing the actual graph when it's greater than 0. So greater than meaning that's why there's an open circle here at 0, and then only on the side where you see the x's are going greater than. So I also want you to notice these are functions. So when you see this right here where they switch over and we jump from this equation up to this equation, you have to have one open and one closed because it's a function. If these are both closed, it wouldn't be a function, right? Because then it wouldn't pass the vertical line test. So let's just look at a little bit more of this. Part of this video on your notes we're not going to be showing, but we'll go through a little bit further so you can hopefully understand how one of these is actually drawn from scratch. But first, let's evaluate function f above. Let me come back to it. From above, if x is 0. If x is 0, then we're going to be using the upper piece, right? The f x minus 2. So when x's are 0, we're using that upper one because x is less than or equal to 0. So basically I'm replacing the 0 So when x's are 0, so remember the function notation would show the function when x is 0 would be a -2. And you can see that on the graph as well. If you look at when on the graph, if I look in here, when x's are 0, there's your -2. Okay, but what I basically did was I just took the equation piece, and when I figured out where the domain was, I just plugged it in and found my answer. Now when x's are 4, now we're using the lower one. Okay, so when x's are 4, now I'm using the 2x plus 1. So now 4 would go in. 2 times 4, that's a sloppy 4, but 2 times 4 is 8, and plus the 1 is the 9. So the function, when the value is 4, comes out as a 9. Now we can't see that on the graph as easily because it comes off the graph, but that's where you can use the equation to make sure that you know what the value is at that x value. So here we want to graph one of these. So again, we have the domain and the range to describe at the end. We'll talk about that in a minute. We also want to see how we break this up. So first, I want to draw my x and y axes. Then I want to look at these two separate pieces and where are they active. So let's first look at the -x minus 4. So -x minus 4, we know that the y-intercept is the -4. And we know our slope would be down 1, forward 1, or up 1 and backwards 1. So normally we would draw a line that would go all the way through here. But now notice my domain. My domain says that this is only active when we are less than 0 on the x. Remember, the x is this right here. Has nothing to do with these numbers all being negative y's. It's all about the x. So then when I see this, I got to rethink of my equation and how I'm going to draw this. So I am not going to see anything, on that other side. And also what I want to do is take out some points. This point is not active. Right? Because that's not part of the domain. And actually, my y-intercept that I first drew is not active. So I want to make sure I take out those pieces. And I need an open circle there. And I wouldn't see anything on that other side because that's when x's are greater than 0. So again, don't get tricked thinking less than 0 is going to make my graph go down, because here's a case where while the graph is going up, because the y's are doing an up and down thing, the x's are the left and right. So x being less than 0 is seeing that side only. Now on the other one, we are only seeing graphing y equals x. So we know that y-intercept would be right here at 0, 0. And this time we close it because we have the greater than or equal to. We still have a 1 slope. So it's going to go to 1, 1, 2, 2, etc., etc. And this would be the picture of that piecewise function. The open at the 0 for the -4, the closed at the 0, which is the part that's the greater than or equal to 0. Now, to write our domain, we still have all real numbers. We can plug in anything we want. Now, here's where we have to think about our range. So what are the values of y's that we are seeing? Well, because these arrows are both going up, I am definitely seeing things from the -4 up, and I'm seeing them going up forever. Okay, so y's are definitely greater than -4. And then the question is it greater than or equal to, or just greater than? Well, because the last bottom one is an open circle, it is only greater than the -4. So the range is just y equals greater than -4. So let's write a piece function based on the graph that we see. So we're going to basically say y equals, we need that little set bracket. We're only using the one side to show that those two expressions are going to go to the whole function. So looking at this left-sided one, well, I can see that the y-intercept is a positive 3. And if I look at my slope throughout this line, I see up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. So it's definitely a 1 slope. So the first one that I'm going to do, it is x plus 3. Now, when are we seeing it happen? Well, we're only seeing it during the domain when x is less than 0. Because of that open circle, I can see that it's not closed. It doesn't have the or equal to part. And these are not always going to be on the 0. I know these are so far only showing on the y-axis. They can easily be moved off of that, and we just got to pay attention to where it's changing. The second one, if I look at, we see the y-intercept is a negative 1. And this time my slope is up 2, right 1, up 2, right 1, up 2, right 1. So in this case, my slope is 2x minus 1. And again, where are we seeing that piece of the graph live? This time we're seeing it at greater than or equal to 1. And that would be our piecewise function for the graph that you see there to the right. So next we want to talk about a step function. A step function is a piecewise function. It is defined though by a constant value. There are no variables to it. So it's talking about looks like a step or a series of steps where it's just a bunch of line segments. So there are no x's that will kind of end up having any kind of a slope except for that 0 slope. So it kind of looks like a staircase. You can see over here that they look a lot more complicated in a sense, but really it's the same concepts, just trying to make sure we understand where are we seeing the function live versus not live, and we have to have those open circles, closed circles to make sure it stays as a function. So writing one of these. So next we want to graph and then write the function of a step function. So we rent a karaoke machine for 5 days. The rental company is charging $50 for the first day. So it's not a by the hour, it's just for the entire day, from start of the day to the end of the day. Then it's $25 each additional day. So write and graph the step function. So what we want to look at is my step function. We have 5 days. So if we think about it, on day 1, it is going to be $50. Okay. Then when you think about that as well, this time our x is going to be greater than 0 days, but less than 1 day. But basically, they're going to charge you for that very first day that you're using it. Then it's going to start going up. So then the next day, it's $75. Now this time it's going to basically start at 1 day and go until the second day. Then it jumps to 100, starts at, once that clock hits that second day, it's going to go on, 125, starts the third day, and then finally 150, would take us to day 5. Okay, so to be able to graph this, we're going to basically just kind of say, what do these look like? So here we have the day, and we're going to go 1, 2, 3, 4, 5 days, and the cost. We're just going to do the cost at, we'll do 25, those scale. And I'm just going to jump up here to 100, and then jump up to the 150. You certainly understand, I think, 75 and 125 are in between those. So then when we graph this, so when we take out that karaoke machine, it starts charging me right from the beginning, right? So right from the beginning, as soon as I get it, it's going to be a charge of $50 for that first day. Okay. Actually, you know what? I'm going to go back here and I'm going to change this, because really, the moment that you take it out, I'm going to put in that or equal to for the 0, because it really is at that point that you take it out, it's charging you. So I'm going to just make sure we make that little change. Then at the end of day 1, we are now jumping up to that 75. And then we're going to be at 75 all the way until the end of day 2. Then it's going to jump up to 100 all the way until the end of the next day. Jump up all the way to the next day. And then lastly, on day 5, all of that day, it is going to be at 150. So you can see that it looks like a staircase. It looks like it's just going up these constant values all the way over. It's not per hours. It's just each day it's that amount. It jumps to the next amount instantly when you start the new day. So that is a step function. Now, the rest of your video is showing writing absolute functions. We're not going to get into this year, so I'm not going to go on with that last example. I do think it's important to see this piece right here. So when we looked at the absolute value function of, the function of the absolute value of x, we talked about how it created that V-looking graph, right? Where it has that symmetrical look around the vertex. So in a way, you can still think about our absolute value functions as piecewise functions, because you could look at this side and write it as the negative x when you see x's are less than 0. And then all of a sudden it switches to here. And that's the positive x, where the 1 slope and a y-intercept of a 0, only when that's happening. So you can write this function as a piecewise, but we also talked about how to do it just as a regular function. It's obviously not a linear function here, whereas this would be a piecewise of 2 linear expressions kind of coming down for one of them, and this one going up in a nice straight line. This last piece down here, we're not going to worry about. Don't worry about any of that on how we are writing the absolute value functions of that. So hopefully the piecewise functions, they take a little bit of getting kind of squared away in our heads on how the domain is affecting where the live piece of our pieces are. But we'll talk about it in class a little bit further. We'll do some practice on some of them. And if you have any kind of questions, please feel free to ask when we do the review in class or when we start working on the activities.